What if I told you that right now, at this very moment, there's an object hurtling through our solar system that shouldn't exist according to everything we thought we knew about how comets work? And what if I told you that a single photograph of this object has cosmologists, astrophysicists, and planetary scientists scrambling to rewrite decades of established theory? On November 16th, 2024, astronomers captured something extraordinary. The comet designated 3I Atlas, where 3I means the third interstellar object ever confirmed to visit our solar system, did something that breaks our models, not bends them, not challenges them, breaks them completely. Here's what happened when astrophotographer Michael Geiger took a detailed image of this comet. He captured something that made Dr. Daryl Seligman at Cornell University literally stop mid-sentence during a lecture. The coma, that's the fuzzy cloud of gas and dust surrounding a comet's nucleus, was glowing with an intensity and structure that violates the fundamental physics we use to predict comet behavior. The spectroscopic data showed chemical signatures that shouldn't be possible for an object with 3I Atlas's trajectory and supposed composition. Dr. Seligman, who helped identify the first confirmed interstellar object, Oumuamua, back in 2017, said something chilling in his preliminary analysis. If these readings are correct, we need to fundamentally reconsider what we think we know about planetary formation, not just in our solar system, but across the entire galaxy. Think about that for a second. One photograph, one object, and suddenly the textbooks might be wrong. But here's what's going to blow your mind as we go deeper. This isn't just about a comet. This is about the possibility that our solar system has been visited by something that formed under conditions we've never observed before, carrying chemical evidence of stellar processes we didn't think were possible. And the implications stretch far beyond astronomy into the very question of how common our type of planetary system really is in the universe. Before we dive into this cosmic mystery, do me a favor, smash that like button if you're ready to have your understanding of our solar system completely transformed. And subscribe, because over the next 3 hours, we're going on a journey that connects quantum mechanics, galactic chemistry, the formation of life itself, and what this mysterious visitor might tell us about our place in the cosmos. Also, drop a comment telling me what country you're watching from, and what time it is where you are right now. I love seeing this global community of curious minds coming together across time zones to explore the universe. All right, let's build the foundation. But I promise you, even the basics here have surprising twists that most people don't know. First, what actually is an interstellar object? Think of it like this. Imagine you're standing in a massive city with millions of buildings, and most people spend their entire lives moving between buildings in their own neighborhood. That's like planets, asteroids, and comets that formed in and remain bound to our solar system. They're the locals. Now imagine someone who was born in a completely different city, thousands of miles away, who's just passing through your city on a road trip and will never return. That's an interstellar object. It formed around a completely different star, got ejected through some violent process, and now it's traveling through the galaxy. When it passes through our solar neighborhood, we get a brief window to study chemistry and physics from an entirely different stellar environment. Here's the twist, though. Until 2017, we had never definitively confirmed a single interstellar object. Not one. Not in the entire history of astronomy. Think about how insane that is. We built our entire understanding of planetary formation based exclusively on stuff that formed in our solar system. It's like trying to understand human culture by only studying one isolated village that's never had contact with the outside world. Then came Oumuamua in October 2017, and everything changed. Dr. Karen Meach at the University of Hawaii's Institute for Astronomy was part of the team that first identified its hyperbolic trajectory. That's the mathematical term for an orbit that proves an object came from interstellar space and will escape back into it. Oumuamua was weird from the start. cigar-shaped or pancake-shaped, depending on the analysis, tumbling in ways we didn't expect, and showing non-gravitational acceleration that we still can't fully explain. Some scientists proposed it was venting gas like a comet. Others suggested it might be an extremely porous fractal aggregate. And yes, a few even suggested it could be artificial, though that last idea remains highly speculative and not supported by most evidence. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered 2I Borisov II confirmed interstellar visitor. This one was easier to understand because it looked and acted like a comet. It had a tail, it had a coma, it was venting gas as it heated up approaching the sun. Scientists were almost relieved because 2I Borisov fit our models. It was strange in composition, showing carbon monoxide concentrations, unlike solar system comets, but at least it was playing by the rules of comet physics. And then 3I Atlas showed up, and the rules went out the window. Here's what you need to understand. When a comet approaches the sun, we can predict with incredible accuracy what should happen. As the ice in the nucleus heats up, it sublimates, turns directly from solid to gas without becoming liquid first. This venting process creates the coma and tail. We have sophisticated models that account for the comet's size, composition, distance from the sun, and rotation rate. These models have been refined over decades and tested on hundreds of comets. They work, they're reliable, until they suddenly weren't. The image captured by Michael Geiger on November 16, 2024, showed 3I Atlas with a coma structure that was far too bright, far too asymmetric, and producing spectral lines, chemical signatures that didn't match what should be venting from an ice and rock body at that distance from the sun. Dr. Michelle Bannister at the University of Canterbury, New Zealand, who specializes in the composition of small solar system bodies, reviewed the spectroscopic data and noted the presence of molecular emissions that require either much higher temperatures than the comet should be experiencing, or chemical compositions that we've never observed in any comet before. Think of it like this. Imagine you're baking cookies and you have a recipe that's worked perfectly thousands of times. You know exactly what temperature the oven should be, what ingredients go in, and what the cookies should look like when they come out. Then one day, you follow the exact same recipe, but when you open the oven, the cookies are glowing blue and floating. That's not a small deviation. That's a signal that something fundamental about your understanding of baking is wrong. Either the oven is different than you thought, the ingredients are different than they appear, or the laws of baking themselves don't apply in this case. That's where we are with 3I Atlas. But here's where this story gets even more mind-bending. And I want you to really pay attention to this next part, because it's going to change how you think about what's happening. The weirdness of 3I Atlas might not be a bug in our understanding. It might be a feature that tells us something profound about how planetary systems form throughout the galaxy. What if the objects we've been studying in our solar system for centuries are actually the weird ones, and 3I Atlas is showing us what's normal everywhere else? Hold that thought, because we're about to go deep. Let me ask you a provocative question. What if everything you think you know about comets is based on a cosmic accident, the specific conditions of our solar system's formation, and doesn't actually apply to most planetary systems in the galaxy? To understand why 3I Atlas is so troubling to scientists, we need to understand what comets actually are and how they're supposed to behave according to established physics. And I promise you, even this basic explanation has twists that will surprise you. Comets are often called dirty snowballs, but that's misleading. A better analogy: think of them like cosmic freezers that have preserved the chemical conditions of the early solar system. When our solar system formed about 4.5 billion years ago from a collapsing cloud of gas and dust, the temperature varied dramatically based on distance from the forming sun. Close to the sun, it was too hot for volatile compounds like water, carbon monoxide, ammonia, and methane to condense into solid ice. But beyond a certain distance, what we call the frost line or snow line, which was roughly where the asteroid belt is now, these compounds could freeze solid. Comets formed in the outer reaches of the solar system, where these ices could survive. They incorporated not just water ice, but also frozen carbon dioxide, carbon monoxide, ammonia, methane, and complex organic molecules. Then, through gravitational interactions with the forming giant planets, many of these icy bodies were either flung into the distant Oort-Clouda, spherical shell of trillions of comets surrounding the solar system, or into the Kuiper belt beyond Neptune. Now here's the critical physics. When a comet's orbit brings it close to the sun, solar radiation heats the surface. The ices don't melt, remember. We're in the vacuum of space, so there's not enough pressure for a liquid phase. Instead, the ices sublimate, turning directly from solid to gas. This creates jets of gas and dust that form the coma and tail. Dr. Paul Westman at the Planetary Science Institute spent decades developing the models we use to predict this behavior. The key parameters are the comet's heliocentric distance, how far from the sun it is. The composition of the ice's water ice sublimates at different temperatures than carbon monoxide or methane. The comet's rotation and surface features jets can be directional based on where active vents are located. The dust-to-gas ratio, how much rocky material is mixed in with the ice. These models work beautifully for solar system comets. In fact, they work so well that we can predict the brightness and appearance of returning comets years in advance. When Comet Halley returned in 1986, the predictions were spot on. When Comet Hale-Bopp graced our skies in 1997, its behavior matched expectations. When Comet Isan broke apart approaching the Sun in 2013, we understood exactly why. The thermal stress exceeded the structural integrity of the nucleus. This isn't guesswork. This is rigorous physics backed by thermodynamic calculations, spectroscopic observations, and spacecraft missions like ESA's Rosetta mission to Comet 67P Churyumov-Gerasimenko, which orbited a comet for 2 years and even landed a probe on its surface. So when scientists observed 2I Borisov in 2019, they applied these same models. And with some adjustments for its unusual carbon monoxide content, the models worked. Dr. Stefano Bagnullo at the Armagh Observatory and Planetarium in Northern Ireland led spectroscopic studies that showed 2I Borisov had a different carbon monoxide to water ratio than solar system comets. It was more carbon monoxide rich. But the physics of how it vented that material was exactly as predicted. That was comforting. It suggested that while the composition of materials might vary between planetary systems based on the chemistry of their parent stellar nebula, the basic physics of how comets behave was universal. And then the 3I Atlas image came in. The coma was too bright by roughly a factor of 3 to 5 compared to what the models predicted for an object of its estimated size at that heliocentric distance. But it wasn't just brighter. It was brighter in the wrong ways. The spectral lines showed emission features that require specific excitation conditions. Without getting too deep into quantum mechanics, when molecules absorb energy and then re-emit it as light, they do so at very specific wavelengths that act like fingerprints. The energy required to excite these molecules to emit at the observed wavelengths was far higher than solar radiation at that distance should provide. Think of it like this. You have a musical instrument that plays specific notes when you pluck the strings with specific amounts of force. You know exactly how hard you're plucking, and you can predict exactly what notes should play. But then the instrument starts playing notes that would require you to be plucking much harder than you actually are. Either the instrument is different than you thought, or there's another source of energy you haven't accounted for. So what are the possible explanations? This is where it gets really interesting, because each possibility breaks something we thought we understood. Maybe the comet is much smaller than we estimated, which would mean it should heat up faster, but that creates other problems with how bright it appears. Maybe it has an exotic composition we've never encountered, with ices that sublimate at much lower temperatures, but that would require formation conditions unlike anything in our solar system. Maybe there's an internal heat source, but what could that be? Radioactive decay? Tidal heating from its rotation? Some other mechanism we haven't considered? Or maybe, and this is the possibility that keeps Dr. Seligman up at night, maybe our models are built on assumptions that only apply to our specific solar system, and 3i Atlas is showing us what's normal for planetary systems that formed under different conditions. Let's explore that rabbit hole. Here's what will blow your mind. The chemistry available to build planets and comets depends entirely on what generation of star you're orbiting. And most stars in the galaxy are very different from our Sun. Our Sun is what astronomers call a population-ized star, meaning it's relatively young, only 4.5 billion years old, and relatively metal-rich. In astronomy, anything heavier than helium is called a metal, even though we're talking about elements like carbon, oxygen, nitrogen, silicon, and iron. The Sun formed from a nebula that had been enriched by the deaths of previous generations of stars. When massive stars explode as supernova, they forge heavy elements in the incredible temperatures and pressures of the explosion and scatter them into space. When smaller stars die, they gently puff off their outer layers, also enriching the interstellar medium. This means the cloud of gas and dust that collapsed to form our solar system already contained the raw materials for rocky planets, and the complex chemistry of life: carbon, nitrogen, oxygen, phosphorus, sulfur, and all the rest. But here's the critical point. Earlier generations of stars didn't have this advantage. Population 2 stars formed when the universe was younger, from gas that had been enriched by fewer previous stellar generations. And the very first stars, population 3 stars, which have never been directly observed, but must have existed, formed from primordial gas that was essentially just hydrogen and helium, left over from the Big Bang. Now, why does this matter for 3i Atlas? Because the chemical composition of the nebula that forms a planetary system determines what kind of planets and comets can form. Dr. Edwin Bergen at the University of Michigan has done groundbreaking work on how the carbon-to-oxygen ratio in stellar nebulae affects the chemistry of forming planets. If you have a higher carbon-to-oxygen ratio than our solar system, you get more carbon-rich compounds like carbon monoxide, methane, and even exotic things like silicon carbide and graphite in your planet-forming disk. If you have a lower ratio, you get more water and carbon dioxide. But it goes even deeper than that. The metallicity of the parent star affects how much dust forms in the protoplanetary disk, which affects how efficiently planets can form, which affects the dynamics of how smaller bodies get scattered into interstellar space. Here's the analogy. Imagine you're trying to build structures using only the materials available in your local environment. If you live in a forest, you build with wood. If you live in a desert with clay, you build with adobe bricks. If you live in an area with abundant stone, you build with rock. The architectural principles might be similar, but the actual materials and therefore the details of construction are completely different. You wouldn't expect a wooden house to behave exactly like a stone house in a fire or earthquake. The same principle applies to planetary systems. Comets that formed around a metal-poor star might be compositionally different in ways we can't even predict because we have no local examples to study. Now, let's add another layer of complexity. The radiation environment of the parent star matters enormously. Our Sun is a G-type main sequence star, relatively stable, with a specific spectrum of radiation. But the most common type of star in the galaxy is actually the M dwarf, or red dwarf smaller, cooler and redder than the Sun. These stars have completely different ultraviolet and X-ray outputs, which affects the photochemistry in their protoplanetary disks. Photochemistry is just the chemical reactions driven by light. When ultraviolet photons hit molecules in a protoplanetary disk, they can break molecular bonds and allow atoms to recombine in different ways. This is how complex organic molecules form in space. But the specific wavelengths of UV light matter. Dr. Karen Bieberg at Harvard-Smithsonian Center for Astrophysics has shown that the UV environment affects things like the water content in forming comets, the abundance of organic molecules, and even the ratio of different isotopes of elements. So if 3I Atlas formed around a star with a very different UV environment than our Sun, which is likely since it came from interstellar, space it might contain ice mixtures we've never encountered. These exotic ices might sublimate at different temperatures, might absorb solar radiation more efficiently, might produce gas species that our models don't account for. Think about it. We've been building our understanding of comets by studying examples from one stellar environment, our own. That's like trying to understand Earth's entire biodiversity by only studying organisms in a single tide pool. You'd get some things right about how life works, but you'd miss the incredible diversity of adaptations to different environments. So here's the mind-bending question. What if most comets in the galaxy don't look like solar system comets? What if our comets are the weird ones, and 3I Atlas is giving us our first real glimpse of what's normal out there in the galaxy? But there's an even more provocative possibility that some scientists are beginning to whisper about, and it connects to one of the deepest questions in science. How did life begin? Stay with me, because this next section is going to take us from comet chemistry to the origin of life itself. Let me tell you something that's going to sound insane. Some of the most complex organic molecules ever detected in space weren't found in the lab. They were found in comets. And now, with 3I Atlas, we might be looking at organic chemistry from a completely different stellar environment. This could rewrite our understanding of how the building blocks of life form in the universe. First, let's establish something surprising. Comets are rich in organic compounds. And I don't mean simple stuff. I mean complex prebiotic molecules. The ESA's Rosetta mission detected glycine, an amino acid, on Comet 67P. It found phosphorus, a key ingredient for DNA and cell membranes. It found a wide array of complex carbon-based molecules, including formaldehyde, methanol, ethanol, and even more complex things like polyoxymethylene, which can act as a slow-release source of formaldehyde. Dr. Catherine Altwig at the University of Bern, who led the analysis of data from the Rosina instrument on Rosetta, made a shocking statement after analyzing the full dataset. What we found was much more complex than we expected. The comet contains the raw materials for life, and in some cases, molecules that are already on the path toward biological chemistry. Think about what that means. Comets, these frozen relics from the formation of planetary systems, are carrying incredibly complex chemistry. They're not just frozen water, they're chemical factories. Here's the mechanism. In the cold, dark regions of protoplanetary disks and in interstellar space, ice grains act as surfaces where atoms and simple molecules can meet and react. When a hydrogen atom sticks to a grain of ice, and then a carbon monoxide molecule sticks nearby, they can react to form formaldehyde. Formaldehyde can then react with other molecules to build more complex organics. This happens incredibly slowly. We're talking timescales of thousands to millions of years, but it happens. And here's the kicker. This process is affected by radiation. Cosmic rays, high-energy particles from exploded stars penetrate into protoplanetary disks and interstellar space and provide the energy to drive these reactions. Ultraviolet light from nearby stars can also contribute. The specific mix of radiation determines what molecules can form. So comets from different stellar environments might have very different organic chemistry depending on where they formed. A comet that formed in a dense stellar nursery with lots of nearby young, hot stars pumping out UV radiation would have different chemistry than a comet that formed in a quiet region of the galaxy with lower radiation levels. Now, here's where this gets directly relevant to 3I Atlas. The spectroscopic data is showing emission lines that suggest organic molecules. But the specific species and their abundances don't match solar system comets. Some researchers have noted features that could indicate more complex nitrogen-bearing organics than we typically see. Dr. Jennifer Bergner at the University of California, Berkeley, who studies the formation of organic molecules in icy environments, points out something crucial. The organic chemistry in comets is exquisitely sensitive to formation conditions. Temperature, radiation environment, the availability of different atoms, all of this affects what molecules you get. An interstellar comet is potentially our only way to sample organic chemistry from a completely different stellar environment. Think of it like this. Imagine you're a chef and you've been cooking your entire life using ingredients from one specific farm. You know those ingredients intimately, how they taste, how they interact, what dishes you can make. Then one day, someone brings you ingredients from a farm on the other side of the world, grown in different soil, different climate, different water. They might be the same types of vegetables and grains, but they taste different. They cook differently. They combine in unexpected ways. That's what we're dealing with when we study interstellar comets. But here's where this connects to the origin of life. There's a hypothesis in astrobiology called panspermia, the idea that the building blocks of life, or even life itself, might be transported between planetary systems on comets and asteroids. The traditional view was that life started on Earth from molecules present in Earth's early environment. But what if Earth was seeded with complex organic molecules from space? We know that comets bombarded the early Earth during the period called the Late Heavy Bombardment. About 4 billion years ago, the inner solar system was pummeled by asteroids and comets. These impacts delivered enormous quantities of water and organic molecules to Earth. Some scientists argue that this extraterrestrial delivery might have been crucial for jump-starting life. Now, extend that idea. If interstellar comets are also occasionally captured by planetary systems, then organic chemistry from one stellar system could potentially seed life in another. We're not talking about living organisms surviving the journey. That's extremely unlikely. But complex prebiotic molecules? That's actually plausible. Here's what should blow your mind. If interstellar comets like 3I Atlas carry complex organic chemistry from their home stellar systems, and if such comets are occasionally captured by other planetary systems, then the organic chemistry that led to life on Earth might not be purely local. We might be at a molecular level partly alien. Let that sink in for a second. The molecules that make up your DNA, the amino acids in your proteins, the lipids in your cell membranes, some of their chemical precursors might have been synthesized around a completely different star and delivered to Earth by ancient comet impacts. You're not just made of stardust in the poetic sense that the atoms in your body were forged in stellar nucleosynthesis. You might be made of stardust that was chemically processed in an alien protoplanetary disk, frozen into a comet, ejected into interstellar space, captured by our young solar system, and delivered to Earth in a cosmic game of chemical telephone that spans light years and billions of years. And 3I Atlas might be giving us our first detailed look at exactly this process in action. But let's pump the brakes for a second and ask a more fundamental question. How did 3I Atlas get here in the first place? How do objects get ejected from their home planetary systems to become interstellar wanderers? Because the answer to that question tells us something profound about how common planetary systems like ours actually are. To understand this, we need to talk about the violent, chaotic early history of planetary systems. Our solar system today seems pretty calm and orderly planets on stable orbits, mostly circular, all going around the sun in the same direction. But it wasn't always this way. In fact, it was once a complete demolition derby. Dr. Alessandro Morbidelli at the Observatoire de la Côte d'Azur in France is one of the world's experts on planetary system dynamics, and his work has revolutionized our understanding of the early solar system. According to the NICE model, named after the city where it was developed, the giant planets in our solar system didn't form where they are now. Jupiter, Saturn, Uranus, and Neptune were originally in a much more compact configuration, and their orbits were not as stable as they are today. About 500 million to 600 million years after the solar system formed, something dramatic happened. The giant planets underwent a period of orbital instability. They started gravitationally interacting with each other and with the disk of icy planetesimals beyond Neptune. These interactions caused the planets to migrate. Jupiter moved slightly inward, while Saturn, Uranus, and Neptune moved outward. This migration was catastrophic for the small bodies in the solar system. As Neptune plowed outward through the primordial Kuiper belt, it scattered countless icy objects. Some were flung into the inner solar system, causing the late heavy bombardment that cratered the moon and inner planets. Some were sent into distant, eccentric orbits in the Oort cloud, and some, here's the key point, were accelerated to such high speeds that they escaped the sun's gravity entirely and became interstellar objects. Think of it like this. Imagine a crowded skating rink where everyone's moving in more or less the same direction. Then suddenly, a few really large skaters start changing direction unpredictably. The smaller skaters get bumped and jostled. Some get knocked into the walls. Some get knocked into different skating patterns. And some get knocked so hard, they fly right off the rink entirely. That's what happened to countless comets and asteroids during the chaotic early solar system. Now here's what this tells us about 3I Atlas. It was almost certainly ejected during a similar period of instability in its home planetary system. The specific dynamics of the ejection depend on the architecture of that system. How many giant planets it had, how massive they were, how their orbits evolved. Dr. Sean Raymond at the Laboratoire d'Astrophysique de Bordeaux has run thousands of simulations of planetary system formation, and his results are eye-opening. He finds that essentially every planetary system with giant planets goes through a phase of dynamical instability. It's not an occasional thing, it's nearly universal. And during these instabilities, a significant fraction of the system's small bodies, anywhere from 10% to 90%, depending on the system architecture, get ejected into interstellar space. Think about the implications. If this is common, then interstellar space should be full of these ejected objects. And indeed, when astronomers have done the math, they estimate there should be trillions of interstellar objects passing through the galaxy at any given moment. The problem is, they're incredibly hard to detect, because they're small, dark, and moving through the vast emptiness of space. We only detect them when they happen to pass close enough to the sun to be illuminated, and when we happen to be looking in the right direction at the right time. Oumuamua, 2I Borisov, and 3I Atlas are likely just the tip of an enormous iceberg. For every interstellar object we detect, thousands or millions pass through unnoticed. But here's where it gets really interesting. The properties of these interstellar objects tell us about the planetary systems they came from. A comet like 3I Atlas, with its unusual composition and behavior, might come from a planetary system that's very different from ours. Perhaps one that formed around a different type of star, or one where the giant planets underwent a particularly violent instability, or one where the chemistry of the protoplanetary disk was exotic. So every interstellar object is like a messenger from an alien planetary system, carrying information about conditions we can't observe any other way. We can detect exoplanets, planets around other stars with telescopes, and we've found thousands of them. But we can't directly sample their composition or the composition of comets from those systems. Interstellar objects are the only way to get physical samples of material from other stellar systems. And that's why 3I Atlas is so precious. That single photograph that breaks our models isn't just a scientific puzzle, it's a Rosetta Stone for decoding the chemistry and dynamics of an alien planetary system. Everything we learn from 3I Atlas tells us something about conditions around another star, probably dozens or hundreds of light years away, in a stellar environment we've never directly studied. But there's a darker possibility lurking here, and it's one that some scientists are starting to take seriously. What if 3I Atlas isn't just unusual because of where it formed? What if it's unusual because of what happened to it on its journey through interstellar space? Let me ask you something that sounds simple, but has a complex answer. What happens to a comet when it spends millions or billions of years traveling through interstellar space? Your first instinct might be, nothing, it's just frozen in the vacuum of space. But that's wrong. Interstellar space is not empty, and it's not quiet. Objects traveling through the galaxy are constantly being bombarded by radiation and particles that alter their surface. Chemistry in ways we're only beginning to understand. This process is called space weathering, and it's crucial for understanding 3I Atlas. Let me paint the picture of what a comet experiences during an interstellar journey. First, there's the radiation. Cosmic rays, high-energy protons, and heavier atomic nuclei, accelerated to nearly the speed of light by supernova shockwaves, and other violent cosmic events constantly pepper the galaxy. These particles are so energetic that they can penetrate deep into solid material, breaking chemical bonds and creating new compounds. When a cosmic ray hits an ice grain in a comet, it can split water molecules into hydrogen and oxygen radicals, which can then react with other molecules to form things like hydrogen peroxide and ozone. It can break down complex organics or, paradoxically, create new complex organics through radiation chemistry. Dr. Chris Bennett at the University of Hull in the UK has studied the effects of cosmic ray bombardment on ice analogs in the lab. His team takes mixtures of ice that mimic comet compositions, blasts them with high-energy particles that simulate cosmic rays, and analyzes what compounds form. The results are startling. You get chemistry that doesn't happen anywhere else. Molecules form that would never form under normal conditions because the energy input from cosmic rays is so high. Now imagine this process continuing for millions of years as a comet drifts through interstellar space. The outer layers of the ice become chemically altered, creating a weathering rind that's compositionally different from the pristine interior. This rind might be more rich in complex organics, more depleted in volatile ices like carbon monoxide, and more enriched in radiation-damaged compounds. Second, there's the interstellar medium itself, the thin gas between the stars. It's incredibly tenuous, less than 1 atom per cubic centimeter on average. But when you're moving through it at 26 kilometers per second, like 3I Atlas is, those atoms hit your surface with significant energy. It's like sandblasting in ultra-slow motion. Over millions of years, this can erode surface material and further alter surface chemistry. Third, and this is fascinating, there are interstellar dust grains. These are tiny particles, mostly made of silicates and carbonaceous material, floating through the galaxy. When you're traveling at tens of kilometers per second and you hit one of these grains, it's a microscopic impact that vaporizes both the grain and a bit of your surface. Countless such impacts over time create a heavily modified surface layer. Think of it like this. Imagine you put a new car in a field and leave it there for 100 years without any maintenance. Rain, wind, sun, temperature changes, impacts from hail and debris, all of these gradually weather the car. The paint fades, rust develops, the tires crack, organic material accumulates. If someone found that car a century later and tried to determine what it was like when new by only examining the exterior, they'd get a lot of things wrong because the exterior has been so heavily modified by weathering. The same principle applies to interstellar comets. The surface we see when they enter our solar system might be very different from the interior, and both might be different from what the comet was like when it was first ejected from its home system. So when we observe 3I Atlas and measure its composition and behavior, we're seeing a combination of the original composition determined by its formation environment around another star, chemical modifications from radiation processing during its interstellar journey, possible erosion and alteration from collisions with interstellar dust. Now, Here's the complicating factor. We don't know how long 3I Atlas has been traveling through space. Based on its velocity and trajectory, astronomers can calculate that it came from the direction of a certain region of the sky, but they can't pinpoint which star it came from or when it was ejected. It could have been wandering for just a few million years, or it could have been in transit for hundreds of millions of years. And here's what should blow your mind. Every interstellar object carries a record of its journey in its chemistry. It's like a geological record, but written in molecular changes rather than rock layers. If we could analyze the depth profile of 3I Atlas, how the chemistry changes from the surface to the interior, we could potentially reconstruct its exposure history and learn how long it's been in interstellar space. But we can't do that from Earth. We can only observe the surface material that's currently venting as the comet heats up approaching the sun. It's like trying to read a book by only looking at the cover. You get some information, but you're missing the full story. This is one of the great frustrations of interstellar object research. We have these incredibly valuable messengers from other stellar systems passing right through our cosmic backyard, and we can only study them superficially. We can't land on them, can't drill into them, can't bring samples back to Earth for detailed analysis. At least not yet. Before we go deeper into what 3I Atlas might be telling us, let's talk about something that doesn't get enough attention: the sheer technological challenge of studying these objects, and why that single photograph is so valuable. When Michael Jagger captured that image of 3I Atlas on November 16, 2024, he was working at the edge of what's possible for ground-based astronomical photography. Think about what he had to do. Identify a faint, fast-moving object against the background stars. Track it precisely as it moved across the sky. Collect enough light to reveal details of the coma structure. And do all of this through Earth's turbulent atmosphere, which blurs and distorts the image. The fact that he succeeded is a testament to modern astronomical technology, sophisticated tracking mounts, sensitive CCD cameras, advanced image processing software. But it's also a reminder of how difficult this work is. Professional astronomers have it somewhat better with large telescopes and space-based observatories, but they face different challenges. Telescope time is precious and competitive. You have to write proposals, get them approved by committees, and then hope the weather cooperates on your scheduled observation nights. And when you're studying an object that's moving and changing as it approaches the sun, you're racing against time. Dr. Matthew Knight at the U.S. Naval Research Laboratory, who has observed numerous comets, including interstellar visitors, describes the challenge. With an interstellar comet, you often don't know what you have until it's already entering the inner solar system. By the time you've identified it, characterized its orbit, and realized it's something special, it might be just weeks away from perihelion, its closest approach to the sun. You have a very limited window to gather data, and if you miss it, that object is gone forever. This is exactly what happened with Oumuamua. It was discovered as it was already leaving the inner solar system. By the time astronomers realized how special it was already too faint to study in detail. It's now too far away to observe with any telescope we have, and it will never return. Everything we'll ever know about Oumuamua comes from those few weeks of observations in late 2017. With 2I Borisov, astronomers had more time. It was discovered earlier in its approach, giving months for detailed observations. But even so, there were fundamental questions that couldn't be answered because of technological limitations. And now, with 3I Atlas, we have another brief window of opportunity. Every observation is precious because we're collecting data that will never be available again once the comet swings around the sun and heads back into the depths of space. But here's the thing that keeps planetary scientists up at night. What if we could do more? What if instead of just observing interstellar objects with telescopes, we could send a spacecraft to intercept one? This is not science fiction. It's been seriously studied. In 2019, after Oumuamua's discovery, A group of scientists and engineers, led by the Initiative for Interstellar Studies, proposed a mission concept called Project Lyra. The idea was to design a spacecraft that could be rapidly launched and use gravitational assists from planets to chase down an interstellar object and fly past it at close range with scientific instruments. The engineering challenges are immense. Interstellar objects are moving at very high speeds relative to our solar system, typically 20 to 40 kilometers per second. To match velocities with such an object for a rendezvous mission is currently beyond our propulsion capabilities. But a fast flyby might be possible, especially if we catch the object early enough in its approach. The scientific payoff would be extraordinary. Instead of observing from hundreds of millions of kilometers away with telescopes, you could image the nucleus at high resolution, measure its composition directly with mass spectrometers, analyze the coma and tail up close, and potentially even collect dust particles from the tail to return to Earth. Think about what we could learn from that. We could measure the isotopic ratios of elements, which tell us about the nuclear processes in the star that the comet formed around. We could identify organic molecules that are impossible to detect spectroscopically. From Earth, we could determine the exact size, shape, and rotation of the nucleus. We could map the distribution of ices and rocky material. But here's the catch. Such a mission would require years of advance warning to design, build, and launch the spacecraft. And we typically only discover interstellar objects weeks or months before they make their closest approach to the sun, unless we get lucky. Unless we set up an automated survey that constantly scans the sky and could detect interstellar objects years in advance while they're still far from the sun, giving us time to mount a mission. This is actually being worked on. The Vera C. Rubin Observatory, which is set to begin operations soon in Chile, will survey the entire visible sky every few nights with a massive camera, detecting faint, moving objects. Astronomers estimate it could detect dozens of interstellar objects per year, potentially including some with years of lead time before they reach the inner solar system. Imagine what we could do with that capability. Imagine if we'd had 5 years of warning about 3I Atlas. We could have launched a mission, intercepted it, and directly sampled material from another stellar system. We're standing at a threshold. In the next decade or two, interstellar object science is going to transform from a field where we passively observe rare, lucky encounters to one where we actively hunt these objects and potentially send spacecraft to study them up close. And that's when we'll really start to understand what 3I Atlas is trying to tell us. Let's shift gears and talk about something that's simultaneously encouraging and deeply weird: the statistics of interstellar objects. Before Oumuamua was discovered in 2017, astronomers had predictions about how common interstellar objects should be. Based on models of planetary system formation and ejection dynamics, they estimated we should be able to detect somewhere between 0.1 and 10 interstellar objects per year with our survey capabilities at the time. That's a huge range of uncertainty, but it gave us a ballpark. Then Oumuamua showed up, one data point. Then 2I Borisov in 2019, 2 data points. Now 3I Atlas in 2024, 3 data points over 7 years. That's right, in the middle of the predicted range, which is encouraging. It suggests our models of planetary system dynamics are roughly correct. The galaxy is indeed full of ejected debris from planetary system formation, and these objects occasionally pass through our stellar neighborhood. But here's where it gets weird. Dr. Gregory Laughlin at Yale University, who has studied the statistics of interstellar objects, points out something troubling. If you look at the detailed properties of the 3 confirmed interstellar objects we've found, they're incredibly diverse. Oumuamua was tumbling, elongated, showed non-gravitational acceleration, and had no obvious coma or tail. 2I Borisov looked like a fairly normal comet, but with unusual carbon monoxide abundance. And now 3I Atlas is a comet that's behaving in ways that break our models. Three objects, three completely different sets of properties. It's like if you were trying to understand cars by studying three random vehicles, and the first one was a motorcycle, the second was a Tesla, and the third was a monster truck. You'd learn something about vehicles, but you'd have a hard time drawing general conclusions about what's typical. This extreme diversity could mean several things. Maybe planetary systems are incredibly varied in their compositions and dynamics, and we're just seeing a natural sampling of that diversity. Or maybe the processes that eject objects from planetary systems select for unusual objects. Perhaps only the weird ones get ejected, while more typical objects remain bound to their home stars. Or maybe space weathering during the interstellar journey transforms objects in diverse ways, depending on how long they've been traveling and what they've encountered. We simply don't know yet. We need a larger sample size. And that's why every new interstellar object is so precious. Each one adds to the statistical picture and helps us understand what's typical versus what's exceptional. But there's an even more mind-bending statistical question. How many interstellar objects have already passed through our solar system before we had the technology to detect them? Think about this. Modern astronomical surveys that could detect interstellar objects have only existed for about 20 years. The first truly comprehensive all-sky survey, the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, started operations in 2010. That's when we really gained the capability to routinely detect faint, fast-moving objects that might be interstellar. Before that, we were essentially blind to these objects unless one happened to pass very close to Earth and become bright enough for amateur astronomers to notice. Given how rare close approaches are, we almost certainly missed countless interstellar visitors throughout human history. Dr. Avi Laub at Harvard, who has been a vocal advocate for interstellar object research, estimates that hundreds or even thousands of interstellar objects have passed through the inner solar system during recorded human history, and we never knew they were there. They came, they passed by, they left, and we were oblivious. Some of them might have been extraordinary, perhaps even more unusual than Aumuia or Three-Eye Atlas. We'll never know. But going forward, our detection capabilities are improving rapidly. The Rubin Observatory, I mentioned earlier, will be a game changer. It will detect not just dozens, but potentially hundreds of interstellar objects per year. Within a decade, instead of having 3 examples to study, we might have hundreds or thousands. And here's what should blow your mind. Once we have that statistical sample, we'll be able to map out the chemical and physical diversity of planetary systems across the galaxy without ever leaving our solar system. Every interstellar object is a sample from a different stellar environment, a different chemical composition, a different history. Collectively, they're a survey of galactic planetary science. It's like if you were trying to understand the diversity of Earth's ecosystems, and animals from all over the world occasionally wandered into your backyard. You couldn't visit the Amazon rainforest or the African savanna, but you could study the creatures that showed up in your yard and infer what conditions must be like in those distant places. That's what we're doing with interstellar objects. We're studying samples of distant planetary systems that conveniently come to us. And Three-Eye Atlas, with its model-breaking behavior, is telling us that the diversity out there is even greater than we imagined. But let's get back to the specifics of what makes Three-Eye Atlas so puzzling, because there's one aspect we haven't fully explored yet: the thermal problem. Remember how I said the coma of Three-Eye Atlas is too bright and showing spectral signatures that require more energy than solar radiation should provide? Let's dig into exactly why that's so problematic and what it might mean. The thermodynamics of comets is actually pretty straightforward in principle. A comet nucleus at a certain distance from the Sun receives a certain amount of solar radiation. Some of that radiation is reflected back into space. The amount depends on the reflectivity, or albedo, of the surface. The rest is absorbed and heats the surface. As the surface heats up, ice begins to sublimate. Sublimation is an endothermic process, meaning it absorbs heat. This cools the surface, creating a balance between heat input from the sun and heat loss from sublimation and thermal radiation. You can calculate the equilibrium temperature based on these factors, and from the temperature, you can predict the sublimation rate of different ices: water, carbon monoxide, carbon dioxide, methane, etc. This is well understood physics. Dr. Yanga Fernandez at the University of Central Florida has spent his career making these calculations for comets, and they work remarkably well for solar system comets. You can predict the gas production rate, the brightness of the coma, the appearance of the tail-all from these thermal models, combined with knowledge of the comet's size and composition. But 3I Atlas doesn't fit. The brightness and spectral features suggest gas production rates that are too high for the equilibrium temperature at its distance from the sun. It's as if the comet is hotter than it should be. There are a few possible explanations, and each has profound implications. Possibility 1. Exotic ices. Maybe 3I Atlas contains ices that are far more volatile than anything we have in solar system comets. Water ice sublimates significantly at temperatures above about 200 Kelvin. Carbon monoxide sublimates at much lower temperatures, around 25 Kelvin. It's extremely volatile. But what if there are ices or ice mixtures that are even more volatile, that start venting vigorously at temperatures where water ice would barely be active? Such exotic ices would require formation conditions we've never directly observed, perhaps an extremely cold protoplanetary disk, or one with unusual chemical composition. If this is the answer, then 3I Atlas formed in an environment that's fundamentally different from where solar system comets formed, and our models need to account for a much wider range of possible comet compositions. Possibility 2. Internal heat. What if the comet has an internal heat source that's adding to the solar heating? There are a few ways this could work. One is radioactive decay. If the comet incorporated a high abundance of radioactive isotopes when it formed, those could be decaying and releasing heat over time. But the amount of radioactive material would have to be surprisingly high to produce the observed effects, and we don't know of any formation mechanism that would concentrate radioactive elements in comets to that extent. Another internal heat mechanism is crystallization of amorphous ice. Ice can exist in two forms: crystalline, which is the orderly, structured form we're familiar with, and amorphous, which is a disordered, glassy form that occurs when water vapor freezes very rapidly at very low temperatures. When amorphous ice warms up and transitions to crystalline ice, it releases heat. If 3I Atlas contains a lot of amorphous ice that's now crystallizing, that could provide internal heat. But here's the problem. Crystallization happens at specific temperatures, around 130 Kelvin, and once it happens, it's done. You can't keep releasing heat from crystallization indefinitely. So this mechanism could only work if 3I Atlas is just now reaching the temperature where crystallization begins, which would be a remarkable coincidence in timing. Possibility 3. Surface properties. Maybe the surface of 3I Atlas is darker than typical comets, meaning it absorbs more solar radiation. A very dark surface with an albedo of just a few percent could heat up significantly more than a brighter surface. But this creates a different problem. We can estimate the albedo based on the brightness of the nucleus and the amount of sunlight it's reflecting. The albedo would have to be so low that it would be darker than charcoal, darker than asphalt, darker than almost anything we've measured in the solar system. That's possible. Some asteroids have extremely low albedos, but it would be very unusual for a comet, which typically has a mix of ice and dust that isn't quite so dark. So we're left with three possibilities, none of which is comfortable. Exotic composition that requires formation conditions we don't understand, internal heating from mechanisms that seem unlikely, or surface properties that are more extreme than typical comets. Or maybe, and this is what some researchers are starting to suspect, it's a combination of all three. Maybe 3I Atlas has unusual composition, has been modified by space weathering to have a very dark surface, and has some internal heat source we haven't fully considered. The thermal mystery is still unsolved, and that single photograph that started all of this is at the center of the puzzle. That image captured the moment when 3i Atlas revealed that it doesn't play by our rules, and scientists are still scrambling to figure out what new rules apply. But the thermal mystery connects to something even deeper, something that gets to the heart of how we do science. Let me show you what I mean. Here's a question that might seem philosophical, but is actually deeply practical. What does it mean when our models break? How do we know whether we've made a mistake in our calculations, or whether nature is showing us something genuinely new? This is the situation facing scientists with 3i Atlas, and it's worth understanding because it reveals how science actually works, which is often very different from how people think it works. The popular image of science is that it's about certainty, about proven facts and immutable laws. But that's not quite right. Science is actually about models, simplified representations of reality that help us make predictions. A good model captures the essential features of a phenomenon and allows you to predict what will happen under new conditions. Newton's law of gravity is a model. It says that the gravitational force between two objects is proportional to their masses and inversely proportional to the square of the distance between them. This model worked brilliantly for centuries, predicting planetary motions with extraordinary accuracy. But then astronomers noticed something weird. Mercury's orbit didn't quite match the predictions. There was a tiny discrepancy in how Mercury's orbit precessed rotated slowly over time. The discrepancy was small, just 43 arcseconds per century, but it was real and reproducible. At first, astronomers tried to modify the model by proposing an undiscovered planet inside Mercury's orbit that was perturbing it. They even gave this hypothetical planet a name, Vulcan. They searched for it extensively. It didn't exist. It took Einstein's general theory of relativity to explain Mercury's orbit. Newton's model wasn't wrong exactly. It was incomplete. It worked beautifully in most situations, but broke down in the strong gravitational field close to the sun, where relativistic effects become important. The same pattern has repeated throughout the history of science. Classical physics worked beautifully until we looked at atoms and had to develop quantum mechanics. Euclidean geometry worked perfectly until we considered the geometry of curved spacetime and needed general relativity. Models break when we encounter conditions they weren't designed for. And when that happens, we have a choice: modify the model or develop a new model that encompasses a wider range of phenomena. That's exactly where we are with 3i Atlas. Our comet thermodynamics and chemistry models work beautifully for solar system comets. They've been tested and refined on hundreds of examples. But they break when applied to 3i Atlas. Dr. David Jewett at UCLA, who discovered the Kuiper Belt and has studied comets for decades, addressed this exact issue in a recent talk. When a model fails, the first question is always whether we've made a mistake, a calculation error, a wrong assumption, a measurement problem. You check and recheck everything. But if the failure persists, you have to entertain the possibility that the model's assumptions don't apply in this new regime. That's both frightening and exciting for a scientist, because it means there's something new to discover. So with 3i Atlas, researchers are going through this process right now. They're checking their calculations, verifying the observational data, looking for measurement errors. But the data is holding up, and the anomalies persist. This suggests we're at a genuine boundary of our models, a place where our understanding, built on solar system comets, doesn't extend to interstellar visitors. And that boundary is telling us something important about the diversity of planetary systems and the range of conditions under which comets can form. Think of it like this. Imagine you're a biologist who has only ever studied mammals. You've developed detailed models of how mammals work: warm-blooded, fur-covered, live, birth, lactation. Your models predict mammalian biology beautifully. Then someone brings you a platypus. It's a mammal, but it lays eggs. It has fur, but also a duck-like bill. It's warm-blooded, but its body temperature is lower than typical mammals. Your models break. Does that mean your models were wrong? No, they accurately described the mammals you studied. But they were incomplete because you hadn't encountered the full diversity of mammals. The platypus expands your understanding of what a mammal can be. That's what 3i Atlas is doing for comet science. It's expanding our understanding of what a comet can be, what compositions are possible, what behaviors can occur. It's revealing that the comets we've studied for centuries might be just one subset of a much more diverse population of icy bodies throughout the galaxy. And that has profound implications. If our solar system comets are not representative of comets in general, then we need to be very careful about drawing conclusions about planetary system formation, organic chemistry delivery, and even the potential for life elsewhere, based solely on what we see locally. The model-breaking moment captured in that photograph is in a very real sense a moment of revelation, a pulling back of the curtain to glimpse a more complex reality than we imagined. But let's get personal now. Let's talk about what this means for you. We're about halfway through our journey, and I want to take a moment to connect all of this abstract astrophysics to something concrete. Your life, your worldview, your place in the universe. Because here's the thing, 3i Atlas isn't just some distant astronomical curiosity. This story, this snapshot that breaks our models, is fundamentally about something that affects how you understand reality and your place in it. Let me explain what I mean. Think about your daily life. You wake up, you go about your day, you interact with people, you worry about your problems, and celebrate your joys. Your world feels local, immediate, bounded by the horizon of your experience. But the truth, the deep, overwhelming truth that 3i Atlas represents, is that you are living in a galaxy of hundreds of billions of stars, most of which have planetary systems, and material from those systems is constantly flowing through space. At this very moment, there are likely dozens or hundreds of interstellar objects passing through our solar system, carrying chemistry from stars you'll never see, from planetary systems that formed billions of years ago. Some of that material ancient particles of interstellar dust is constantly raining down on Earth. You've probably breathed in atoms that originated in another stellar system. The water you drink contains hydrogen atoms, some of which might have been part of ice grains in an interstellar comet. You are, quite literally, made of material that has traveled between the stars. Think about what that means for your identity. You're not just a citizen of your country, or even of Earth. At a molecular level, you're a citizen of the galaxy. The atoms in your body have cosmic addresses, and those addresses span light years. 3i Atlas is a reminder of this connectivity. It's physical proof that the boundaries between stellar systems are permeable, that material and chemistry, and maybe even the seeds of life, move between worlds. And here's where it gets even more personal. The fact that our models break when we study 3i Atlas is a reminder that your understanding of reality is always provisional, always open to revision. You go through life building mental models of how things work, how relationships function, how careers develop, how the world operates. These models work most of the time. But occasionally, something happens that breaks your models, that doesn't fit your expectations, that forces you to expand your understanding. When that happens, you have a choice. You can dismiss the anomaly, rationalize it away, force it to fit your existing worldview. Or you can let it change you, let it expand your conception of what's possible. That's what scientists are doing with 3i Atlas, allowing an anomaly to expand their conception of what comets can be. And that same process of staying open to revision, of updating your models when new data comes in, is something you can apply in your own life. I'm not just talking abstractly here. Think about a time when something happened that challenged your assumptions. Maybe someone you thought you knew well surprised you with an unexpected action. Maybe a career path you were certain about suddenly didn't feel right. Maybe a belief you held turned out to be incomplete or wrong when you encountered new information. Those are your personal 3-eye atlas moments, times when the model breaks and reality reveals itself to be more complex than you thought. The question is, how do you respond? Do you get defensive, dig in, insist that your model must be right and reality must be wrong? Or do you lean in with curiosity, willing to be transformed by the encounter with something genuinely new? The scientists studying 3-eye atlas are leaning in with curiosity. They're excited, not threatened, by the fact that their models break, because they understand that every broken model is an opportunity to develop a better, more comprehensive understanding. You can adopt that same stance in your life. When you encounter something that doesn't fit your expectations, that challenges your worldview, you can view it not as a threat, but as an invitation to grow. And there's something even deeper here about uncertainty and humility. The 3-eye atlas story reminds us that despite all our technology, all our scientific knowledge, all our sophisticated models, we still have enormous blind spots. We're studying the universe from one small planet around one average star in one galaxy, among hundreds of billions. Our perspective is necessarily limited. Recognizing that limitation is not a source of despair, it's a source of wonder. It means there's always more to discover, always something that can surprise us, always the possibility of encountering something genuinely new. And that same principle applies to human knowledge in general. No matter how much we know, no matter how sophisticated our understanding becomes, we're always working with incomplete information, always one surprising observation away from having to revise our models. That should make you both humble and excited. Humble because you recognize the limits of your knowledge. Excited because those limits mean there's always more to learn, always the possibility of being surprised by reality. Now let's take all of this and connect it to probably the biggest question in science. Are we alone in the universe? You might be wondering what 3-eye atlas has to do with the search for extraterrestrial life. The connection might not be obvious, but it's profound, and it touches on some of the deepest questions we can ask. Remember earlier when I talked about how comets deliver organic molecules, and how interstellar comets might carry organic chemistry from one stellar system to another? Let's explore that idea more deeply, because it has implications for how life emerges and spreads through the galaxy. The traditional view of the origin of life, which you might have learned in school, goes something like this. On the early Earth, simple chemicals like methane, ammonia, water, and carbon dioxide were present in the atmosphere and oceans. Energy from lightning, UV radiation, or volcanic activity drove chemical reactions that created more complex organic molecules like amino acids and nucleotides. These molecules accumulated in pools or on mineral surfaces, and through some process we don't fully understand, they organized themselves into self-replicating systems, the first life. This is the primordial soup hypothesis, and it's supported by famous experiments like the Miller-Urey experiment from 1953, where Stanley Miller and Harold Urey showed that running electricity through a mixture of gases could create amino acids. But there's always been a problem with this scenario. The step from simple organic molecules to actual living, self-replicating systems is enormous. It's not just a matter of making amino acids. You need them to link up into functional proteins. You need nucleotides to form RNA or DNA. You need lipids to form cell membranes. You need all of these components to come together in a functioning system that can metabolize, reproduce, and evolve. The probability of all of this happening spontaneously seems vanishingly small. Some scientists have calculated that the odds are so low that life might only emerge once in the entire observable universe, which would make Earth's biosphere a unique cosmic accident. But what if that calculation is wrong because it's based on an incomplete picture? What if life doesn't have to start from scratch on every planet with the simplest possible chemicals? This is where comets and interstellar panspermia come in. If comets deliver not just simple organics, but complex prebiotic molecules that are already partway along the path from chemistry to biology, then the improbability problem becomes less severe. You're not starting from scratch. You're starting from a more advanced starting point. And if interstellar comets are part of this delivery mechanism, then organic chemistry developed in one stellar system could potentially seed life in another. This doesn't mean living organisms are traveling between stars. That's extremely unlikely given the harsh radiation environment of interstellar space and the timescales involved. But complex organic molecules are much more robust and could potentially survive the journey. Dr. Chandra Wickramasinghe, working with the late Sir Fred Hoyle, has been one of the strongest proponents of this idea for decades. They've argued that the complexity of organic molecules found in comets and interstellar space is difficult to explain unless life is widespread in the galaxy and biological material is being spread via comets and dust grains. Now, I should be clear. This idea remains controversial, and most scientists are skeptical that actual biological material is being transported this way. But the idea that complex prebiotic organic molecules are shared between stellar systems via interstellar objects is becoming more mainstream as we learn more about the organic richness of comets. And 3I Atlas fits into this story because its unusual chemistry might be telling us about organic synthesis in a completely different stellar environment. If the organic molecules in 3I Atlas are different from what we find in solar system comets, that tells us that different stellar environments produce different organic chemistry, which means the path to life might be different in different planetary systems. Think about the implications. If every stellar environment produces its own unique mix of organic molecules, then every planetary system where life emerges might be starting from a different chemical toolkit. That could mean life takes very different forms in different systems, not just superficial differences like blue aliens versus green aliens, but fundamental differences in the chemistry of metabolism, the structure of information-carrying molecules, maybe even whether life is carbon-based at all. Alternatively, if interstellar objects are mixing chemistry between systems, then maybe there's a kind of chemical homogenization happening on galactic scales. Maybe the organic chemistry available for life to emerge from is actually more similar across different planetary systems than we'd expect, because interstellar comets are distributing molecules and potentially biasing all planetary systems towards similar starting conditions. We don't know yet which scenario is correct, but 3I Atlas is giving us data to start addressing these questions. And here's the most profound implication. If interstellar objects do play a role in distributing organic chemistry, or even seeding life, then life on Earth might be related at a deep molecular level to life elsewhere in the galaxy. Not because of intelligent aliens visiting and deliberately seeding life, but through natural processes of cosmic chemistry. Let that sink in. If interstellar panspermia is real, then your cells, your biochemistry, your DNA might be the result of chemistry that occurred not just in our solar system, but across multiple stellar systems. The molecules that make you alive might carry a history that spans light years and billions of years, connecting you to stellar environments you'll never see. You would be, in a very literal sense, a child not just of Earth or even of the Sun, but of the galaxy itself. And every time we study an interstellar object like 3I Atlas, every time we analyze its chemistry and try to understand its origin, we're reading pages from that galactic story, the story of how matter and chemistry and potentially even life flows through the cosmic ecosystem. That's not just science. That's answering one of the deepest questions you can ask. Where do I come from? And the answer might be, from farther away than you ever imagined. Let's talk about where this field is going, because we're living at a pivotal moment in the history of astronomy. We're transitioning from an era where interstellar objects were theoretical curiosities to an era where they're regular visitors we can study in detail. Over the next decade, several developments are going to transform this field. First, detection is about to get much better. The Vera C. Rubin Observatory I mentioned earlier will be a revolution. Its massive camera will image the entire visible southern sky every few nights, detecting anything that moves or changes. Astronomers estimate it will find somewhere between 20 and 100 interstellar objects per year once it's fully operational. Think about what that means. In just a few years, we could go from having 3 confirmed interstellar objects in all of human history to having hundreds or even thousands. That's enough for real statistics, for patterns to emerge, for us to start categorizing these objects and understanding what's typical versus what's exceptional. Second, spectroscopic capabilities are improving. The James Webb Space Telescope, which is already operational, has the sensitivity to study the chemical composition of interstellar objects in unprecedented detail, assuming we can get telescope time when one passes through. Future space telescopes will have even better capabilities. Ground-based spectroscopy is also advancing rapidly. Extremely large. Telescopes like the European Extremely Large Telescope and the 30-meter telescope will have the light-collecting power to study faint, distant objects with high spectral resolution. This means we'll be able to identify specific organic molecules, measure isotope ratios, and characterize the detailed chemistry of interstellar comets. Third, and this is the big one, we're seriously planning interstellar object intercept missions. The European Space Agency has been studying a mission concept called Comet Interceptor, which would launch a spacecraft that waits in deep space at the L2 Lagrange point, ready to intercept a newly discovered long-period comet or interstellar object on short notice. NASA and other agencies are considering similar concepts. The idea is to have a spacecraft on standby that can be quickly redirected to whatever interesting object appears, rather than having to design, build, and launch a mission from scratch after the object is discovered. If we can actually intercept and fly past an interstellar object with scientific instruments, the data we'd collect would be transformative. We'd directly sample dust from another stellar system. We'd image the nucleus at close range. We'd measure the composition and structure of the coma with in situ instruments. But there's an even more ambitious possibility being discussed. Could we actually capture an interstellar object and bring it back to Earth for laboratory analysis? This sounds like science fiction, but it's been seriously studied. The key is to find a small interstellar object, maybe a boulder-sized chunk of material, rather than a kilometer-scale comet that happens to have a trajectory and velocity that makes it accessible. With advanced propulsion systems, possibly including nuclear thermal propulsion or solar sails, it might be possible to rendezvous with such an object, capture it, and slowly bring it back to Earth orbit over the course of years or decades. The scientific payoff would be immeasurable. Instead of analyzing interstellar material with the limited instruments we can fit on a spacecraft, we could bring it back and study it in the world's best laboratories. We could section it, analyze it with electron microscopes, measure isotope ratios with incredible precision, search for complex organics, maybe even look for preserved records of interstellar radiation damage that would tell us about the environment the object traveled through. Dr. Andreas Eng at the Initiative for Interstellar Studies has calculated that such a mission is technically feasible with technology we could develop in the next 20 to 30 years, assuming we commit the resources. The challenge is economic and political rather than purely technical. So within your lifetime, maybe within the next couple of decades, we might go from having just a few telescope observations of interstellar objects to actually having interstellar material in laboratories on Earth that scientists can study directly. That's an extraordinary prospect. It means questions we can only speculate about today might have definitive answers in the near future. What's the typical composition of comets in the galaxy? How diverse are planetary system chemistries? How common are exotic ices and unusual organic molecules? These questions could transition from theoretical puzzles to empirical science. And think about what that would mean for your understanding of the universe. Right now, everything we know about the cosmos beyond our solar system comes from light photons that have traveled across space to our telescopes. We can learn a lot from light, but there's a limit to what spectroscopy can tell us. But if we can actually hold a piece of another stellar system in our hands, analyze it atom by atom, study its structure and composition with every tool we have, that's a completely different level of knowledge. That's going from astronomy to comparative planetary science on a galactic scale. And 3I Atlas might be remembered as one of the key objects that sparked this revolution, the comet that broke our models and showed us we needed to think bigger, prepare better, and invest in the infrastructure to study these cosmic messengers properly. We're in the final stretch now, and I want to pull everything together and show you the big picture, what 3I Atlas really means, not just for astrophysics, but for how we understand our place in the cosmos. Throughout this journey, we've explored a lot of technical details: thermodynamics, orbital mechanics, spectroscopy, organic chemistry. But at its core, this story is about something much more fundamental. It's about the moment when we realize that our backyard is not isolated, that we live in a connected cosmos where material and chemistry, and potentially even the seeds of life, flow between stellar systems. For most of human history, we thought we were the center of everything. The Earth was the center of the universe, with everything revolving around us. Then Copernicus showed that Earth orbits the sun, not the other way around. Then we learned the sun is just one star among hundreds of billions in our galaxy. And our galaxy is one among hundreds of billions in the observable universe. Each of these revelations was a step toward understanding our cosmic insignificance. The fact that we're not central, not special, not the point around which everything revolves. But there's another thread running through this same history, and it's equally important: the growing understanding of our cosmic connectedness. We're made of elements forged in the cores of ancient stars. The atoms in our bodies have been recycled through multiple generations of stellar birth and death. The water we drink, the oxygen we breathe, the carbon in our cells, all of it is stardust, quite literally. The discovery of interstellar objects like 3I Atlas adds another layer to this story of connectedness. We now know that material doesn't just flow through time, from ancient stars to new planetary systems, but also through space, between stellar systems. The galaxy is not a collection of isolated planetary systems evolving independently. It's an ecosystem where material circulates, where chemistry developed in one location can seed processes in another, where the boundaries between here and there are permeable. And that changes everything. It changes how we think about planetary system formation. Instead of treating each system as a closed system, we need to account for contamination or enrichment from interstellar material. It changes how we think about the origin of life. Instead of assuming life must emerge independently in each system, we need to consider that chemistry from one system might give life a head start in another. It changes how we think about the search for life. Instead of looking for exact Earth analogs, we need to consider that life might emerge from diverse chemical starting points influenced by different stellar environments and potentially by mixing of chemistry between systems. And it changes how you should think about yourself. You're not just a biological organism that evolved on Earth. You're a temporary pattern in matter that has flowed through the cosmos for billions of years. Matter that carries in its very atoms a history of stellar processes and galactic mixing. 3I Atlas is a messenger carrying information about a stellar environment you'll never visit, chemistry from a place that might be hundreds of light years away. When astronomers analyze its spectrum and try to understand its composition, they're reading a message written in atoms and molecules, a message that traveled for millions of years to reach us. And that message is, you're not alone in the darkness. The galaxy is full of planetary systems, full of chemistry, full of processes that might parallel the processes that led to life on Earth, We're all connected through the flow of matter and energy across space and time. Now, I want to be clear. I'm not suggesting there's anything supernatural or mystical about this. This is physics and chemistry, natural processes following natural laws. But the implications are profound even without invoking anything beyond materialism. Because what it means is that the story of how you came to exist is not just the story of Earth's history, or even our solar system's history. It's a galactic story that involves stellar systems you'll never know about, chemical processes in environments you'll never experience, mixing and evolution of matter on scales that dwarf human experience. You contain within you the history of the cosmos. The calcium in your bones was created in a supernova. The iron in your blood was forged in the core of a massive star. The water in your cells might contain hydrogen that was part of an interstellar comet. The organic molecules in your DNA had precursors that formed in the cold darkness of protoplanetary disks or interstellar space. You are the universe looking at itself. You're made of cosmos stuff, and that cosmos stuff has been on an incredible journey to get here, to this moment, to you. And when you look up at the night sky and think about 3I Atlas out there, passing through our solar system carrying chemistry from another stellar environment, you're witnessing that cosmic connectivity in real time. You're seeing the evidence that the boundaries we draw between here and there, between us and them, between our planetary system and other planetary systems, are artificial constructs. At the level of atoms and molecules, it's all one big interconnected system. That's the real significance of that photograph, the snapshot that breaks the model. It's not just about fixing some equations or updating some theoretical frameworks, though that's important. It's about recognizing that reality is more connected, more complex, more magnificent than we imagined. Our models broke because they were built on a limited perspective, the perspective of one planetary system, around one type of star, in one region of one galaxy. They worked beautifully within that limited context, but they weren't universal. 3I Atlas showed us the limits by being different, by carrying chemistry and exhibiting behavior that doesn't fit our local experience. And that's okay. That's how science advances. We build models based on the data we have. When we encounter something new that doesn't fit, we expand our models. And in the process, we expand our understanding of what's possible, what's typical, what the universe is actually like beyond our limited experience. But there's a lesson here that extends beyond astrophysics. Be humble about your models. The mental models you use to navigate life, your assumptions about how things work, how people behave, what's possible, are necessarily based on limited experience. They might work beautifully within the context you've encountered so far, but they might break when you encounter something genuinely new. And when your models break, don't panic. Don't dig in and insist that reality must be wrong. Instead, do what scientists are doing with 3I Atlas. Lean in with curiosity. Examine the anomaly. Ask what it's telling you. Update your models to encompass this new data. Grow. That's the real gift of 3I Atlas, not just what it teaches us about comets or planetary systems, but what it teaches us about the process of learning itself, about staying open to surprise, about maintaining humility in the face of a vast, complex universe that will always have the capacity to surprise us. And there's something empowering about that. Yes, we're small. Yes, we're insignificant in the grand cosmic scheme. One planet around one star in a galaxy of hundreds of billions of stars. But we're the creatures who can recognize that insignificance, who can study objects from other stellar systems and decipher their messages, who can expand our understanding to encompass phenomena we've never directly experienced. We're made of stardust that has become conscious, that has developed science and mathematics and technology, that can look out into the cosmos and begin to understand our place in it. That's extraordinary, and you're part of that story. Every time you look up at the night sky with wonder, every time you ask questions about how things work, every time you update your understanding based on new information. You're participating in humanity's grand project of understanding the universe. 3i Atlas is just one chapter in that ongoing story. There will be many more interstellar visitors, many more anomalies, many more model-breaking moments. Each one will teach us something new, will expand our perspective, will remind us that the universe is larger and stranger and more wonderful than we thought. So here's what I want you to take away from this. You live in an age of discovery. Right now, in your lifetime, we're transitioning from imagining what might exist in the cosmos to actually studying it. Interstellar objects like 3i Atlas are just the beginning. In the coming years and decades, we'll detect more of them, send missions to study them, maybe even bring samples back to Earth. You'll get to witness humanity's understanding of the cosmos expand in real time. You'll see new discoveries that challenge assumptions, new data that breaks models, new insights that transform how we think about our place in the universe. Pay attention, stay curious, keep asking questions, and remember that every model scientific, personal, philosophical is provisional, always open to revision when reality reveals something new. If this journey has sparked something in you, wonder, curiosity, a desire to understand more, then you're feeling exactly what you should be feeling. That sense of awe at the complexity and scale of the universe is not a weakness or a distraction. It's one of the things that makes us human. It's what drove our ancestors to study the stars, and it's what will drive us to keep exploring, keep discovering, keep expanding our understanding. So go outside tonight if you can. Look up at the stars. Think about 3i Atlas out there somewhere, carrying its message from another stellar system. Think about the countless other interstellar objects passing through right now that we haven't detected yet. Think about the chemistry happening in protoplanetary disks around other stars right now. Chemistry that might someday seed life in ways we can't yet imagine. And remember that you're part of this cosmos. You're not separate from it, observing from the outside. You're in it, made of it, connected to it through billions of years of cosmic evolution. The snapshot that breaks the model that image of 3i Atlas captured on November 16th, 2024, is a reminder that we're still at the beginning of understanding the universe. Despite all our progress, all our technology, all our sophisticated models, we're still being surprised by reality. We're still encountering phenomena that don't fit our expectations, that challenge our assumptions, that force us to think bigger. And that's exactly as it should be. The day we stop being surprised is the day we stop discovering. The day our models stop breaking is the day we stop learning. So here's to 3i Atlas, the comet that broke our models and in doing so expanded our understanding. Here's to the scientists working to decipher its message. Here's to the future missions that will study these cosmic messengers up close. And here's to you for taking this journey and opening yourself to wonder at the magnificent, surprising, interconnected cosmos we inhabit. The universe is stranger and more beautiful than we imagined. And there's so much more to discover. Thank you for exploring this with me. If this transformed how you think about your place in the cosmos, hit that like button. Subscribe for more deep dives into the mysteries of the universe, and drop a comment telling me what aspect of this story blew your mind the most. Let's keep the conversation going. Until next time, keep looking up, keep asking questions, keep being amazed.